Okay, here is the series examples I promised you guys earlier today. So we're going to investigate, the following concepts. They're going to ask us here in some of these questions to determine, and I'm going to look at the exact language. Determine whether the series is convergent or divergent. If it's convergent, they want us to find the sum. Okay, so this is essentially where we're at when we first look at these series. And so the first example they give us is something like this. Let me make some space here. Okay. So they give us 1/8 minus 1/4 plus 1/2 minus 1, and then they have this go on forever. Okay, so they give us a series here. This is, believe it or not, it's a series. And stop and think for a second what we studied today. The first series that we studied was geometric, right? So I want you to consider whether this is a geometric series. I'll put that right here. So we're going to put a question mark. It could be geometric, right? We're not sure. We don't know. This would be the A term. This is AR squared, and AR cubed, and that goes on forever. So what this information says to us is we have to check. We may have a geometric series. So this means that A is 1/8. It means AR is actually negative 1/4. So here's AR, and it's negative 1/4. So essentially, the verification requires us simply to solve for R and verify the AR squared term. So since A would be 1/8, we get this equation. 1/8 R is 1/4, and we solve for R, so we can multiply both sides by 8. And what that says is really we have R will be 8/4, or R is the value 2. Okay, now let's verify, and this is what we have to verify here. AR squared needs to be, and we lost a sign here, so let's put that sign there. That's minus, and that's minus 2 then. So negative 8 over, so R will be minus 2. So let's verify. So make sure you have the sign here. Here it is. Okay? And that's why you put the negative there, and the negative is still here and here. So R is negative 2. Okay. So AR squared means the following. A is 1/8, or I should just say this. Let's do it this way. Right? We're going to have to say that AR squared needs to be positive 1/2. So let's verify that AR squared is positive 1/2, and your A value is 1/8. They said R here was negative 2. So here's what we'll get. 1/8 times negative 2 squared better be equal to 1/2 if we have a geometric series. So this is 1/8 times 4 should be 1/2. And this means that 4/8 is 1/2, and that is in fact the case. So this is in fact a geometric series. That's not a question anymore. That's an exclamation mark. So we have a geometric series, and we verified this. So this is verified. Okay, now, because we have a geometric series, what we talked about today, what I proved to you is you will have convergence. In other words, every geometric series will converge to A over 1 minus R. This is the sum, but this is what you need. The absolute value of R has to be smaller than 1. Now, R here, we found, is -2 in this case. So the absolute value of -2 is +2, and ladies and gentlemen, that is not smaller than 1. So what this says here is that we don't have convergence. This is a geometric series, but it diverges. So it's divergent. So here's an example of showing, just by looking at the value R being -2, an absolute value that's bigger than 1. R has to be an absolute value smaller than 1 for a convergent geometric series. And so that's not happening here. So this is how we consider that first question. We have another example that's very similar. And this is 1 plus 0.4 plus 0.16 plus 0.064, and this goes on forever. They want us to know, or to test to see whether this series is convergent or divergent. Now, like I said, we started today looking at our very first series in our life, a geometric series. So I'm going to check. I'm going to see if this is a geometric series. And what that means now is the value A must be 1. So I say A is 1. The value of AR must be 0.4. So I'll say AR is 0.4. We're going to have to verify that AR squared is 0.16. Now, since we said A is 1, this implies now that 1 times R better be 0.4, or really R is 0.4. Okay, this is what we verify now. AR squared needs to be 0.16. So we say AR squared needs to be 0.16. Now, if we plug in the values, A is 1, R is here 0.4. We end up with 1 times 0.4 squared should be 0.16. Now, if you guys don't know, 0.4 squared, you might say, well, what is this? Well, let's multiply. Let's find out what 0.4 squared is. 4 times 4 is 16. 4 times 0 plus 1. And then we count the digits, and sure enough, okay. So this portion is 0.16. And so 1 times that 0.16 is, in fact, 0.16. So what we verified was AR squared is 0.16. And what that means is we have a geometric series. Okay, pretty good. Geometric series. Now, what do we know? Geometric series converges if the absolute value of R is less than 1. And in this case, R is 0.4. So the absolute value of 0.4 is 0.4, and sure enough, that is smaller than 1. So here's our R value. So we just plug that value in, and we find, yeah, 0.4 is smaller than 1. That means their geometric series converges. So we know that this thing converges, and we can say, okay, we have convergence. But they want us to find the sum. And remember, for every geometric series, only for geometric, the sum, that S value, is A over 1 minus R. So use your value here for A being 1 and for R being 0.4 over here. We already found that one. So let's plug those values in. 1.4. So I can use S for sum. I can say that sum is 1 over 1 minus 0.4. And doing some arithmetic, that's 1 over $1 minus 40 cents is 60 cents. That's 0.6. So my S here is going to be 1 divided by, or let's actually do this first. Let's say this is 1 over 6/10. And of course, you know this is 1 divided by 6/10. Finally, this is 1 times 10 over 6 because we multiply by the reciprocal. And then 10/6 is my sum. And I can say, well, does that have to be reduced? Sure. The sum is 5/3. So it's 5 over 3. So ladies and gentlemen, this infinite sum, which is geometric, adds up to 5/3. And there you guys go. So here's some interesting examples. And now let's continue with some more examples of this sort of geometric series here, since that's the first kind of series we talked about today. And notice what they give me here. You got n is 1 to infinity, -6 to the n minus 1 over 5 to the n minus 1. And let me double check to see if that's what we have here. Okay. All right. All right. So here's the deal now. Here's a series. It may be geometric. It may not be geometric. There's a couple of approaches for this. Remember, you say, don't I have to have AR n minus 1 where n is 1 to infinity, or I have n is 0 to infinity, AR to the n? We can have those. So you have a couple of options here. So the question here is going to be, well, what can we do here? Well, I'm going to say a couple of things here. We can approach this two ways. You're going to use algebra to simplify. Right? So notice here, you can't do anything without using algebra. And what I mean by that, you're using properties of exponents. So this will become, using algebra, let's be careful here, right? This is going to become -6 over 5 to the n minus 1 power, just by properties. And now you might say to me, okay, that looks a little bit like a geometric series. That looks a little bit like what we have, because we have here the sum, n is 1 to infinity, -6 over 5 to the n minus 1 power. That looks like we have here n is 1. Here we go, n is 1. We do have that, we have an n minus 1 power here, then that means this must be r. So r value here is -6 over 5. But you then say, well, what is the a value? Well, there's nothing there. Put a 1. So we can say here a is 1. Now, this is what this looks like as a geometric series. And this is kind of nice because you say, well, the absolute value of r here is the absolute value of negative 6 over 5, which is 6 over 5, and that is not smaller than 1. So this is a geometric series, but it diverges. Okay, so there is no finite sum for this geometric series. And all we did is use a property from beginning algebra. If you guys remember, you say, well, what property is that? Well, if you have x over n, y to the n, well, that can be written as xy to the nth power. That's all you use from algebra. It's actually beginning algebra. And you say, but I don't see a power n, I see n minus 1. Well, it doesn't matter if it's n or n minus 1. The same property holds. So we looked at it this way, and we found that this was a geometric series. However, I'm going to say you can also do the following. Let's note, and I kind of like that blue, but let's note, what you could have done is what you've done already. So if you said they give you negative 6 to the n minus 1 over 5 to the n minus 1, plug in n, right? This is negative 6 to the 1 minus 1 over 5 to the 1 minus 1 plus negative 6 to the 2 minus 1 over 5 to the 2 minus 1 plus negative 6 to the 3 minus 1 over 5 to the 3 minus 1, and then this goes forever. I get negative 6 to the 0 power over 5 to the 0 power plus negative 6 to the first power over 5 to the first power plus a negative 6 squared over 5 squared. And you guys can start to see that this means we have 1 minus 6 over 5 plus, we can say 36 over 25 minus the next term. And you can approach this just like you did the prior two, where you have a, and this is AR, and this is AR squared. So you can verify that this is a geometric series. Okay, so this is a big part of what you do in the beginning here. It's a good exercise to verify. Here's what I mean. A is 1 right here. This A value is 1. AR minus 6 over 5. So we can say AR is minus 6 over 5, where A here is 1. Now that implies that R is minus 6/5. So you say, remember, we have to check, we have to verify the next term. We verify that AR squared is a positive 36 over 25. So AR squared will be 36 over 25 here. Now you say, what does that mean? Let's plug in 1 for A, and R is negative 6 over 5. So we end up with 1 times negative 6 over 5 squared should be 36 over 25 if this is in fact geometric. So this is 1 times 36 over 25 should be 36 over 25, and sure enough, that is true. So this is a geometric series, and R here is the value negative 6 over 5. You can say the same thing that you did before. You know simply that the absolute value of that R value is not smaller than 1. In fact, 6/5 is what this is. We already seen it already when we checked this up here. So we already knew, ladies and gentlemen, that R was negative 6/5. So there's actually 2 ways of doing this. One is to use some algebra, like we just did. The other would be to just simply write out the terms of the series and verify the way you did the prior two. So pick your poison or pick your approach. Okay, so anyway, there's another example. So I told you guys earlier today, I have a bunch of really good examples for you to look at. And here is another example. And let me write down the terms here. This is what you're looking at, right? Well, this is the series they give you. And I started to write here for you guys, or not started, I did. I wrote 2 versions of that geometric series that you see in textbooks. Now, this particular second one starts with n is 0, and then the power is just an n. And they're equivalent. They're the same series. So this one starts with 0, and the power is just an n. So if you see that, you think algebraically, wow, that might be 0 ar to the nth power. But then what in the world is r, and what is a? Well, use some algebra. What that means is 1 over the square root of 2 to the nth power, ladies and gentlemen, is the same as 1 over n square root of 2 to the n, which is 1 over square root of 2 to the nth power. So that this particular series really can be described as 0 to infinity, 1 over the square root of 2 to that nth power. So yet again, here's my r, and I could put 1 for a, just like we did in the past. So this says to me a is 1, and r is 1 over the square root of 2, because it's in the definition form. Here's my a. Here's my r. That's the r value. Power n. There we go. This is geometric by definition. Or, if you didn't like that, I mean, I already know it's geometric. If you looked at the terms and you said, I want to look at these terms here. Okay. Well, let me get my computer screen back here. Let's put the password. There you go. Okay. Well, let's just finish this off. We're practically there. Well, the absolute value of r, which is the absolute value of 1 over the square root of 2, which is 1 over the square root of 2. Now, ladies and gentlemen, the square root of 2 is about 1.4. So 1 over 1.4 is actually going to be smaller than 1. So this geometric series is actually convergent. So we can say it's converges or it's convergent. This is what they're asking us to do. And because it's convergent, we need the sum. And you say, okay, this sum here is going to be, again, a over 1 minus r, where the value a becomes 1, and r is 1 over the square root of 2. So s is 1 over 1 minus 1 over the square root of 2, and we're going to find that sum. Now remember what we can do here. We're going to have to subtract this, this fraction. So we're going to write square root of 2 over 2. So s is 1 over the square root of 2 minus 1 over the square root of 2. And we can say 1 divided by the square root of 2 minus 1 over square root of 2, which is really 1 times the reciprocal. So my sum becomes here the square root of 2 over square root of 2 minus 1. And because this converges, this is the finite sum, ladies and gentlemen. So in short, n is 0 to infinity. 1 over square root of 2 to the n adds up to what you see here. Okay, now here's the thing here. Let me remark. When you go back and you say, was this geometric? If you just simply looked at the terms again, right, n is 0, I'm going to use blue. 1 over square root of 2 to the 0, plus 1 over square root of 2 to the 1 plus 1 over square root of 2 squared plus 1 over square root of 2 to the third power. This goes on forever. This is 1. This is just 1 over the square root of 2. 1 over the square root of 2 squared. 1 over square root of 2 cubed, and this goes on forever. If you needed to, just verify. Here's A, here's AR, this should be AR squared. You will in fact find that this is a geometric series if you verify the terms like we've been doing. Meaning set A equal to 1, set AR equal to 1 over the square root of 2, which means R is 1 over the square root of 2, and then you verify the third term that AR squared is 1 over square root of 2 squared. So you do what we've been doing, and notice again, you find A is going to be 1. I think we have it somewhere here. There we go. We already know A is 1, and R was 1 over the square root of 2, and you can find the sum in the same exact way. So there is a couple of ways of looking at this problem. One is by the definition. You might have to do a little bit of algebra, and then the other is simply just doing it by looking at the terms. And that's a good practice for you. And we all learn that way by practicing these things. So, you know, either way is fine, but just make sure you get that practice. Okay, let me look at some more here. So I'm going to look through my notes. And get a few more here that are interesting. Okay, let's do a few more here. Sum pi to the n over 2 to the n plus 1. And now we're going to have n equals 1 to infinity. Okay. Now, you might say, I want to consider the form you're talking about here. You said n is 1 to infinity, AR to the n minus 1, because I notice my index here starts with 1, this starts with 1, and I don't know if this is geometric. Well, there might be some algebra you have to use, but I would suggest here, just look at the terms. Start with n is 1. If that's the case, we get pi to the first power over 2 to the 1 plus 1. Now n is 2. Pi squared, 2 to the 2 plus 1, plus pi cubed, 2 cubed plus 1, plus pi to the 4th, 2 to the 4th plus 1, and then this goes on forever. So you get pi over 2 squared plus pi squared over 2 cubed plus pi cubed over 2 to the 4th plus pi to the 4th over 2 to the 5th, and that's found by simply looking at the terms where we have n is 1, n is 2, n is 3, n is 4. Okay, so I'm going to look at it this way. Now remember, if this is geometric, we have A, AR, AR squared, and this would simply be AR cubed. So we're going to check to see if we have a geometric series. Okay, so the same exact way we've been doing. A, we need to highlight. A is pi over 2 squared, so we're going to write that down. A will be pi over 2 squared. And we also have AR being, let's write that, AR being pi squared over 2 cubed. So we're going to plug in the values here, right? We're going to say, well, what was a to begin with? A was pi over 2 squared. So we're going to find this value of r, ladies and gentlemen. We need r. So pi over that 2 squared, which is a times r, is pi squared over 2 cubed. Solving for r, we could multiply by the reciprocal. So r was going to be pi squared over 2 cubed times 2 squared over pi. And we find r going to be, just using some algebra, pi over 2. Because you're going to use properties here. Remember, pi squared over pi to the first would be pi. And then 2 squared over 2 cubed would be the 2. So we're going to just use algebra here. Properties of exponents. So I got a value for r. We don't know if this is geometric. What we have to verify is the next term. That ar squared needs to be pi cubed over 2 to the 4th. That part has to be verified. So let's write that down. Ar squared needs to be pi to the 3rd over 2 to the 4th so that we know for certain that this is geometric. When you say, what was a? A was pi over 2 squared. Now, what was r? Well, that's pi over 2. That's why we found r. So, altogether, pi over 2 squared times pi over 2 in parentheses squared is pi cubed over 2 to the 4th. So I get pi over 2 squared times pi squared over 2 squared, and that's going to be pi cubed over 2 to the 4th. And sure enough, we did verify that this is the same. So we know, ladies and gentlemen, that the series here is in fact geometric. It's a geometric series. So the absolute value of r needs to be smaller than 1. And so the absolute value of pi over 2, ladies and gentlemen, what do we know? Pi is about 3.14, but divided by 2, that's going to be bigger than 1, so it's not smaller. So this is in fact a geometric series, but it diverges, or we can say it's divergent, diverges, doesn't matter. So here we go. Here's an example. Another interesting example. Okay, let's do something similar, these geometric series. And you have here the sum, n goes to 1 to infinity, e to the n over 3 to the n minus 1. And you might say, hey, this kind of looks like the definition you gave us, where this here is n equals 1 to infinity, and you have this ar to the nth power here. Let me be a little bit clearer here. So we might suspect here that this is geometric. We say, okay, n is 1, we're starting at 1. But we have an r to the nth power. I have an e to the n, but I got this 3 to the n minus 1. So I have an issue here. And at this point here, we can use, again, some algebra. Or we can look at the terms like we've been doing. We could just expand and look at the terms like we've done for quite a few series and go through the verification process if we like. Or we can use some algebra. Now, I'm gonna be a little fancy here with the algebra, ladies and gentlemen, because this course, like every math course, right? I'm gonna take a look at what we have. you need to learn some algebra and some good algebra. So I'm going to try to see if I can do some algebra here for you guys and make this look like what it should be, right? So here's what I want to say. This is e to the n, 3 to the n times 3 to the minus first power. And that will mean that I have 3 e to the n over 3 to the n, which means I have 3 e over 3 to the nth power. All I did was use beginning algebra properties of exponents. I'm going to say that again. Beginning algebra properties of exponents. So that this series is the same series as n goes to 1 to infinity, 3 e over 3 to the nth power. Now, that looks just like the definition. Oops. We made a little mistake. We made a mistake here. I think this has to be, ladies and gentlemen, n minus 1. I can still fix that mistake. We can still fix the algebra. Okay. That was a little easy. I want to make this term here look just like this. And I can. Let me show you how I can do that, ladies and gentlemen. Let me erase some of the algebra here. This algebra was good. If this started with n is 0, let's go back. If this started with n is 0, we're in business. We have the right algebra. That's okay. Let me show off a little bit more with some algebra skills. So if n started with 0, that was the algebra. It starts with 1. Okay, no big deal. Let me show you how you fix this. This is e to the n minus 1 plus 1 over 3 to the n minus 1. Because you see, ladies and gentlemen, right here, I know I have e to the n. And this here, by the way, is negative 1 plus 1 is 0. N plus 0 is just n. So these two are equivalent. This is what I'm going to do. I'm going to use properties. This is e to the n minus 1 times e to the 1 over 3 to the n minus 1. Which means I really have e to the n minus 1 over 3 to the n minus 1, or I have e over 3 to the n minus 1. Okay, now I'm in business. This is here my a, and this is my r. In other words, this is what we're looking at. So the series here, I'll put it in red. N is 1 to infinity, e over 3, n minus 1 is in fact in the form of a Rn minus 1, where n is 1 to infinity. It's in our definition form, where my a value is 3 and my r value is e over 3. So you do need to have, ladies and gentlemen, that n minus 1 if you start with n is 1. You need to have that power, and that's all I did. So I use a little bit of algebra, and I know this is geometric now. So I can say, okay, we have a geometric series. We just have to see if it's convergent or divergent. And you say, how do we know? Well, the absolute value of r needs to be strictly less than 1. So that means here, the absolute value of e over 3. Now, if you guys know, the value of e is about 2.718. Divided by 3, well, absolute value is positive. E over 3, 2.718 over 3 is in fact less than 1. So my r value in absolute value is less than 1. That means we have convergence. So this is a convergent geometric series. So I'm using the definition, and in order to get that, we use some algebra. And they ask us, hey, if it's convergent, what's the sum? Well, my sum formula is A over 1 minus R. So A here again, you say, what is A? Go back. A is not 3. A is E. A is right here. So this is E over 1 minus, and you say, well, what is R? R is right here. It's E over 3. So let's find the sum. And I can replace my 1 here with 3 over 3. And I get E over 3 minus E over 3, which is E divided by 3 minus E over 3. Or we say E times 3 over 3 minus E. So our sum here is going to be 3E over 3 minus E. So this is how we handle some of those geometric series, ladies and gentlemen. And I told you we're going to have some good ones. And we are. Okay. And then some very interesting examples you may want to see, some geometric series, is that, they're going to say, write or convert something like this. 1, 3 with a line as a fraction, right? And sometimes they'll use the formal word for fraction, which is a rational. Okay, and so if you guys recall what this is, 0.13 with that line is actually 13131313, right? Forever. That 1 3 with the line on top means continue this forever. Now, you may not know this, but this is in fact a geometric series. So this is working with some geometric series here. All right. What do we do with this now? Well, how could this be a series? Well, because I take here, let's see if we can do this here for you. Let's change the color here. These first two terms. It's 0.13. Now, what I'm going to do now is I'm going to add 0013. So together, I'm looking at the next 4 terms. And then I'm going to repeat that process. This is going to be plus. Now, 1, 2, 3, 4 zeros, 1, 3. And this goes on forever, this pattern. So it is, in fact, a geometric series. It is an infinite sum. It can be written that way. I'm now looking at the first 6 terms here. So what you guys see is writing 0.13 with that line on top, which just repeats the pattern forever. You wrote this as an infinite sum. And this is, by the way, I'll put it here. It's geometric. And you might say, well, how do you know? Well, let's figure this out. Let's test the terms, right? AR squared. So we're saying A is 0.13. We're saying AR is 0.0013. So AR 0013. So if I plug in 0.13 here, we'll have 0.13 R is 0.0013. And then we can divide both sides now by, because we're solving for R, we're going to verify. Here's what we get. R is 0.0013 over 0.13. So I'm going to use some more arithmetic skills. 13 over, well, this is tens, hundreds, 10,000. And this is 13 over 1000. So I'm writing a decimal as a fraction. And this is a now complex fraction. So this is 13 over 10,000. Okay, let's write it divided by 13 over 100. We'll do an extra step. And now r is 13 over 10,000 times 100 over 13. So here's what we end up getting here. Our 13 cancels. And 100 over 10,000 will leave 100. So r here is 1 over 100. Now we're verifying to see if this is geometric, right? So you say, well, how do we verify? Well, go to the next term. You get AR squared, and you get this with 4 zeros, 1, 3. And let me go back here and change that color because we're going to verify. AR squared is the 4 zeros, 1, 3. Okay. AR squared is 1, 2, 3, 4 zeros, 1, 3. We just have to plug in what A is. And we say, what was A? Go back up here. 0.13. It's right here. And we have r squared. And you go, what's r squared here? Or what's r? Oh, we found r. Sorry. R is right here. So we're going to plug in for r, 1 over 100. And here's what this gives us. 0.13 times 1 over 100 squared better be 1, 2, 3, 4 zeros, 1, 3. And we get 0.13 over 4 zeros. Double check. Okay. I don't know. Just checking this out. Sorry about that. And we'll see what this is. This is 13 over 100 over 10,000. So we'll do some arithmetic. 13 over 100 divided by 10,000 is 13 over 100 times 1 over 10,000. And this gives me 13 over, I got 6 zeros now. 1, 2, 3, 4, 5, 6. So double check here. Now, 13 with 1 over 6 zeros, which really is a million, becomes 0.1. Let's be careful here. This division is in fact going to give me this here, and I can show you why. I got 1, 2, 3, 4 zeros, and then we have 2 more positions here, 1, 3. So this is in fact going to be 1, 2, 3, 4 zeros, 1, 3. Tens, 100,000, 10,000, 100,000, millions position. So double check here, ladies and gentlemen. This is in fact a geometric series. So we just verified this is geometric. And so we know we have convergence when the absolute value of the value r is smaller than 1. Well, what was r? Here we go. R is over here. It's 1 over 100. So the absolute value of 1 over 100 is in fact smaller than 1. We have convergence because this is 1 over 100, smaller than 1. We just have to find what it converges to, the sum. Well, my sum is a over 1 minus r. So go back to your values, a and r. What was a? A here is 0.13 or 13 hundredths. So a is 0.13. What's the radius r? Or r, sorry. That's 1 over 100. So let's see what this sum gives us. And we're going to do some more algebra, more arithmetic. This is 13 over 100 over 1 minus 1 over 100, because that's what R is. Replace 1 with 100 over 100. So my sum is 13 over 100 over 99 over 100. And what you guys will get is this is 13 over 99. And so here's what this means, right? Stop and think again. 0.13 with that line, they're saying is equivalent to 13 over 99. We wrote this as a fraction, this non-terminating decimal, right? We wrote this 0.13131313 forever is really the fraction 13 over 99. Now, I want to show you something here. I'm not sure if I can. Yeah, let me see if I can. If I get a calculator here. Let me see. Do I have a calculator app? I don't have the desktop, so let's see. Let me find a calculator. I don't know. Let's see here. What do we get? 13 divided by 99. So notice this. 13 over 99 is in fact 131313131313 forever. So ladies and gentlemen, this is an example of a geometric series, and this is kind of the stuff that we went over today. Anyway. Okay, let's transition today a bit. Let's transition with some of these examples. And I'm going to give you guys another example here. We did talk today. So let's get this iPad back. We talked about some telescoping series, and let me give you another example. We have this series. N is 1 to infinity, 2 over n squared plus 4n plus 3. Now, they're going to tell us to show that this series converges. Now, I want to make this remark. Right? This is n is 1 to infinity, AR n minus 1. This is not geometric. So what they gave me here, what they gave you guys, this is not a geometric series. Okay, it is not geometric, and that's problematic. Because we proved a formula here for geometric series when it's convergent and divergent, and we found a way to find the sum, so it's not geometric. So if we stop and think about this, we also talked about today telescoping series. And the thing to remember about telescoping series is that the terms will collapse. That's the idea. Your terms collapse. However, if you guys recall, what I said to you is you have a rational right here. I'm going to say to you, what you do here is you use partial fraction decomposition, PFD. And using partial fraction decomposition, you get 2 over n squared plus 4n plus 3. Now, by partial fraction decomposition, you're going to get this equal to 1 over n plus 1 minus 1 over n plus 3. Okay? And you might say, well, why do I need this? Well, this is what's going to happen. We're going to have to, again, consider the sequence of partial sums. All right. So we're going to have to consider the sequence of partial sums. Let's actually write down what this means, because if I go back and say to you, take a look at what this is. Sorry, I got this dog distracting me. I hope you guys don't hear this. Let me yell at the dog. All right, here's what I have here. Let's look at the details. This series is the same series, n is 1 to infinity, 1 over n plus 1 minus 1 over n plus 3. Okay? And let's start to look at some of these series here. So look at some of the terms. So we're going to start with n is 1, so this means I get 1 over 2 minus 1 over 4. This happens when n equals 1. So I can put my parentheses and I can say, let me add. Now let's see what happens when n is 2. We get 1/3 minus 1/5. So far, to let you guys know, nothing is collapsing here, right? So let's see what happens when n is 3 now. We don't have anything collapsing. So we're going to add here. N is 3. That's 1/4 minus 1. Looks like it's 6. And so this is going to keep going. We say what happens when n is 4. Plug in 4 here. We get 1/5 minus n is 4. It looks like it'll be 1/7. Okay. Now what happens when n is 5? Let's get an idea of these terms here so you guys can see. So if n is 5, we get 1/6 minus 1/8. So it looks like it's differing by 2, right? You say, what do you mean differing by 2? Well, here 2 and 4, that difference is 2, and then 3 and 5, that difference is 2, 4 and 6, the difference is 2, 5 and 7, the difference is 2, 6 and 8. We're starting to see some collapsing. Now, this goes on in theory, right, forever. But if I said to you, the sequence of partial sums, and here's how we can define it. Let's do every detail here for you guys. Remember how we define the sequence of partial sums. I have to change my index. I goes to 1 to n, because we're going to call this Sn. So this was 1 over I plus 1, okay, minus 1 over I plus 3. So we start here at 1, and we end at n. That's why it's the sequence of partial sums. This is S1, S2, S3. And so here's what this will look for us. Right? It looks like what we've just noticed. Let's look at the pattern here. 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6 plus 1/5 minus 1/7. And this was n is 4. And let's do another one. 1/6 minus 1/8. This is n is 5. And I'm going to do something here for you guys. I know I'm going to say to you that this thing ends. You say, where does it end? It ends at n. So the question is, what is n now? Right? This is I will be n. So we get 1 over n plus 1 minus 1 over n plus 3. Because my index is now, this is I is 1, I is 2, I is 3, I is 4, I is 5, I is n. And so this is what we see. Okay. Let me maybe move this term here. I'm going to move it a little bit over because we may need the room. 1/6 minus 1/8, and that happens again for I is 5. So I want to point this out to people so that when you start to say, okay, I thought you just said to me, we're going to have some collapsing. We are, because the reason you use, and these problems are specially chosen, partial fraction decomposition, notice there's a difference there. And because you have the difference, some of these terms are going to go away. And the question now is, which terms go away? Well, let's take a very close look. You see, these terms differ by 2. I plus 1 and I plus 3 differ by 2 terms. So when I take a look here, it's going to be, the second term, and then I have to go 2 over the first term. There's a pattern here. So it's like looking at 3 terms all together. Now go to the next one. The second term, 1/5 of the next one, and then go 2 over, that's the first term. And then the second term, again, 2 over the first term. And if I want to see what happens when n is 6 here, well, we're going to have 1/7 minus 1/9 so that we can see what goes away. The second term and then 2 over first term. So as you guys can see here, we're getting a lot of terms collapsing here. And if I decided to, maybe I will. I'll put it down here to say you have I is 7 now. You said, okay, would that give me 1/8 minus 1/10? It will. And you say, what collapses? The second term, 2 over, and the first term. So what eventually happens, ladies and gentlemen, is what is going to be left over is 1/2, 1/3. Those terms are there. But all the other terms, you say, what are the other terms? You know, here, 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 here. They're all going to collapse. This is going to go away eventually as well. This went away to begin with. This went away to begin with. So this is the collapsing part. The real issue is going to be what happens at the end, right? So what are we left with? Well, look at the pattern. Okay, we want to find out what are we left with. So if I see the pattern here, when I just went up to 7, right? Or here's where we're at. Well, I is 6. I is 7. What we're left with, ladies and gentlemen, is the second term when I is 6. And then the what? The very last term when I is 7. That's a big deal. Let me paint that another color here. So let me erase this here for you guys, because that's the pattern here. And I'm going to erase some of this here too, so you guys can see what I'm talking about, right? Here's what I'm talking about. I'm going to add a whole other row for you guys here, right? We have here 1/8 minus 1/10, right? And this happens when I is going to be 7. So let's see here, right? What canceled? The eighth here we talked about. So it's right here. So this is what we're left with, ladies and gentlemen. And I'm gonna get rid of this here. I'm gonna just kind of point that out to you. Just focus on the collapsing part, right? Everything here with this gray and this line. And I see when I stop at 7, I got 2 terms left. This is the term I got left with. This one and this one. This is the second term. And then this is the, let's be careful here. Yeah, this is the second term as well. Okay, I believe so. Okay. So why I say focus on this is because when we go to the end of this, let's say this is now the end, I'm going to say here, let I be, not n, I is n minus 1, and then we're going to see what happens when I is n, because we're looking at the sequence of partial sums. We want to see what collapses and what remains. So when I is n minus 1, plug it in. Right here, n minus 1 plus 1, oh, that's n. 1 over n minus 1 over n plus 2. Plus 1 over n, oh, n plus 1 minus 1 over n plus 3. So remember here, what remains? What's going to happen here is, for the last 2 terms, the second term and the second term will remain. These 2 terms collapse. These are gone because that's been the pattern that we've seen. So looking at, this kind of picture, we can now describe what's left, meaning the sequence of partial sums after everything collapses is that Sn will be 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. Because these terms are what we started with, and these last 2 terms are what we end with. Everything else will collapse. Even this term here eventually here, right? That was what was left, but eventually, when you continue, these terms will go away. But that's what we looked at to deduce the end. So all of this is collapsing. This is why we call it telescoping. So the idea now for you is going to be to use the limit here of Sn, which is now the limit of 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. Now you guys know about properties of limits. This is 1/2 plus 1/3 plus the limit of 1 over n plus 2 plus the limit 1 over n plus 3. This will go to 0. This will go to 0. And then you're left with here 1/2 plus 1/3, which becomes multiply by 3 by 3, multiply by 2 by 2, and we'll get 3/6 plus 2/6, better known as 5/6. This is the sequence of partial sums, and this is the sum. So we have, ladies and gentlemen, convergence. And so to just kind of emphasize that original question, n is 1 to infinity, 2 over n squared plus 4n plus 3 does in fact converge. It converges to 5/6. And there you go. That's another example of a telescoping series. And this is one that converges. So let me give you another example of these. Telescoping. This is going to be a major idea for us. This one says, show that this particular series, n goes to 1 to infinity, natural log 1 plus 1 over n here, diverges. And notice again, this is not, in fact, a geometric series. This isn't geometric. And then you say, but Mr. Judge, I don't see anything, I don't see a subtraction sign, so when I look at all the terms, it's strictly positive. This is adding these terms forever. And you go, how am I going to, right? This is going to be, if I look at this, this is the natural log of 2 plus the natural log of 3 halves plus the natural log of, let's see, n will be 3, 4 thirds, right? And that goes on forever. I know my fractions look weird. 3 halves, 4 thirds. This goes on forever. I don't see anything collapsing. Well, and I can't use partial fraction decomposition, but I can use algebra. Meaning, the natural log of 1 plus 1 over n is the natural log of n over n plus 1 over n, which is the natural log of n plus 1 over n, which is the natural log of n plus 1 minus the natural log of n. So sure enough, this series is the same. Natural log n plus 1 minus natural log of n. And this is just by simply using some algebra properties of logs and really adding, a whole number with a fraction. So now let's look at these terms here, right? See what happens now. This is the natural log of n is 1, that means 2, minus the natural log of 1. So this happens when n is 1. And then you say, okay, but I'm going to also add again. Now n is 2. Natural log of 3 minus natural log of 2. You go, oh, n is 2. Okay, well, what happens now when n is 3? We get the natural log of 4 minus the natural log of 3. Oh, the next value, natural log of 5 minus the natural log of 4 here. And this happens when n is 3, happens when n is 4, but this is an infinite series. This happens forever. So I'm looking at the terms here. So, okay, this is going to go on forever. But I do see some things happening here. But we have to always consider, remember, this is what we're going to need to do. We're going to consider the sequence of partial sums because we're going to have to look at the limit. So consider the sequence of partial sums again. And again, that means change the index. That Sn will be the sum. I goes from 1 to n, natural log I plus 1 minus natural log of I. Another example of telescoping. All right, okay, there we go. So this tells us where to start. And n tells us where to end. So we start here and we end here. So here's what Sn will look like. Sn is the natural log I is 1, natural log 2 minus natural log 1, plus natural log 3 minus natural log 2, plus natural log 4 minus natural log 3, plus natural log 5 minus natural log 4, plus natural log 6 minus natural log 5. Now notice my index. I is 1, I is 2, I is 3, I is 4, I is 5. So we notice the index here. Now let's see what in fact is collapsing here. Okay, so we want to see what's collapsing for us. Because even though we didn't stop at n yet, right? We have to end at n. I just want to see what that pattern is. So notice this. Natural log 2, the first term of the first pair and the last term of the second pair are going away. You see, these differ by really one term. You got I plus 1 and I. They differ by 1. That's why you see 2 and 1 and 3 and 2 and 4 and 3. So these are pretty close. This is going to be easier than the last one. So let's go look at the next pair here. The first term of the first pair, the last term of the second pair. The first term of the first pair, the last term or second term of the second pair. First term of the first, and then the last term of the second. So everything's going away, ladies and gentlemen. And so if I say to you, well, how does this end? Well, I have natural log of a number minus natural log of a number. And maybe, let me do a couple of things so people can really see this. Because you're really looking at here, if you want to know the truth, you're looking at the ending right here. Here's in some ways how this just ends. I can just say, go all the way up to, let's change that color. Natural log, we're going to say this is n plus 1 minus natural log of n. Remember, this is when I equals n. And so what will happen is this last term goes away, just like you're seeing here when n is, or I is 5. You're going to be left with this term. So altogether, you say, but I'm left with, don't forget, Mr. Judge, you got a minus natural log 1 out here. You do. So here's what I'm saying to you. Sn is minus natural log 1 plus the natural log of n plus 1. But you know natural log 1 is actually 0, so negative 1 times 0 is 0. So the sequence of partial sums, ladies and gentlemen, is actually natural log n plus 1. So you are seeing here the ending in some sense right there. That's what I'm talking about. Just change that I being 5 to I is n, and there's the ending, because everything else collapses. You've seen the pattern. They go away. So you might say, okay, what do we do with this? The sequence of partial sums, we take the limit. So the limit, as n goes to infinity, of Sn is the limit of the natural log of n plus 1, right? And this limit of sequence of partial sums, ladies and gentlemen, is infinity. This diverges. So because the sequence of partial sums diverge, so does the series. The series diverges. And this is what we had to do. They said to us originally, show that this particular series diverges. That's what we just did. We really mean to show, look at the sequence of partial sums. But you're probably going to have to do a little bit of algebra so that we can get a collapsing phenomena occur, so that we can actually see Sn, that sequence in closed form. We can now find that limit. So here's another good example of what we talked about today. So you got a couple of those kind of series here. And then I'm going to say to you guys, let's recall something important here. One of the last things that we ended with today was the test for divergence. This is something you're going to really want to know like you know your name. And here's the test. If the limit of an, remember, you're looking at a series. Here's a series. If the limit of an is not 0 or does not exist, then we know the series equals infinity. You say, what does that mean? the series diverges. So we're testing a series to see if it in fact diverges. Now I'm going to look for my notes for some good examples of this. We already seen one today, but let's give you some more. Yeah, we looked at this one today. How about let's try another one here. So here's what they can ask us. The sum of maybe n plus 1 squared over n times n plus 2. N is 1 to infinity. We still have to see whether the series converges or diverges here. Now, here's what I'm going to say. We're going to try to use this test for divergence. In other words, here's my AN, right? And we're going to change that color. So I want to look at the limit here of AN. N plus 1 squared over n plus 2. So when I look at this limit, I'm going to use algebra. I'm going to FOIL the numerator. So I get n squared plus 2n plus 1 over n squared plus 2n. Okay, so I'm going to use that very famous phrase I like using. Use algebra. Alrighty. Now this is a Calculus 1 question. You divide really again by the highest power of the variable in the denominator, and that here is n squared. So we divide every term by the n squared. If you guys remember, divide n squared by everything. You go, oh, we can finally fit that in. We can hardly fit that in. Limit n goes to infinity. 1 plus 2 over n plus 1 over n squared. Everything over 1 plus 2 over n. So we're going to have to take this limit, and you guys know the limit's going to be, by properties of limits, 1 over 1 are just 1. So what I just showed for you here for you guys is that the limit of an is 1. And that certainly is not 0. So we just showed that the limit here is not equal to 0 for an. Now, what does that mean? That means that the series diverges. This is the divergence test. So what we can say here is, you say exactly that. The series diverges by the test for divergence, or divergence test, whatever you guys want to say, however you want to phrase it. Because you just showed that the limit of an is not 0. That's how we use this very, very infamous fact that we talked about today. So here's a good example of that. And, you know, there's some questions like that. And let me double check here. Yeah, here's, see if we have any more. Another example. I'm not sure if we did something like this today, but maybe. Sum. I can see in our book n over 2n plus 5. N is 1 to infinity. And remember, this is my an. So we're going to look at the limit here of an, which is the limit of n over 2n plus 5. N goes to infinity. Remember, this is now a calculus 1 question. Divide by the variable with the highest power in the denominator. This is going to be n. 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 The limit 1 over 2 plus 5 over n. Now, what's that limit going to be? That limit is 1/2. This 1/2 is not 0. Because it's not 0, what do we say? The series diverges by the, let's rephrase that, divergence test. Divergence test, test for divergence, whatever you want to use. Just know that that limit of an is not 0. And I want to say to you guys, this is a very important fact. And another thing I didn't get to, what I really wanted to say to you, we have some properties of series here. So I want to actually give them to you now. Some properties of series because, you know, they're in some homework questions. Here's how it starts. Let sum an and sum bn be some convergent series with C a constant. Okay, so here's what you can have, I guess. 1. You can add them. So here's a property of summation. And of course, this also converges since each one of these converge. So if you add two finite numbers together, the answer is really finite, right? Right? As they're saying here, these are convergent series. The second thing is take the difference. An minus bn. There's a difference. Sum an minus sum bn. Well, if these numbers are both finite, then the difference of two finite numbers is also finite. Because we have convergence. This is what that means, right? Sum an is finite, and the sum bn is finite. And the last thing that we didn't get to, or the last property there, was if I take a constant times this, pull out the constant, and guess what? This is also finite as well. Anyway, so here's some properties of series that were there. And then I would say to you, what's an example? Let's give you an example. This is a very simple kind of thing, illustrating the properties, right? Here's a series, 5 over n minus 1 plus what? I think we did one of these today. Oh, I think we did this 1/2 to the end today, right? So here's a series. We want to show that this converges or diverges, right? So by the properties, we have a summation property. So we're going to add these separately. We're going to have two different series. Two series. Sum 1/2 to the n is 1 to infinity. Okay, because we have a sum here. Here's a sum. Pull out your constant. So this can be written as 5 times the sum, n is 1 to infinity, 1 over n minus 1, plus the sum, n is 1 to infinity, 1/2 to the n. So here's what we really are getting at by properties of series here. I need to know both of these answers. I answered both of these today. Today we found that this sum was 1. We had convergence. And let me go back and double check our notes. Okay, it was under series. So let's check that. Let's get the computer back. So let's check this. Go back. We did something similar like that. Okay. What am I looking for? 1/2 to the, this is, I'm going to do that. I'm going to put a +1. Good, it's plus and that equals 1. So let me do that now. Show you guys. Well, I'm going to put plus and that's 1. We're going to use this. Okay, this is plus. And the sum was 1. And then that 1/2 to the n. Oh yeah, there we go. No, that's not it. It was geometric. Telescoping. 1/2 to the n. Oh, here it is. That sum was what? Here is 2. So that sum is 2. So we did those earlier. All right. Here's what we're going to do. We're going to make sure that we're using the same ones. And so, yes, this was 1 and this was 2. So with these 3 properties, and I can prove these properties to you, they're kind of not that hard to prove. I mean, all of these properties. The answer now to this more complicated sort of series, this is 5 times 1 plus 2, just by using those properties. 5 times 1 plus 2 is 5 plus 2, better known as 7. So ladies and gentlemen, this summation here is equal to the finite value 7. And notice this is an infinite sum. This goes to infinity. And this is found by just using properties, the 3 properties that we gave you guys up there. Okay, pretty good example. But that's what they want you to do. And again, proving these things, it's not that hard. If you said, okay, let me just prove 1 maybe and say to you, well, how does that work, right? You say, oh, here's really how this is. This is not that hard to do, right? Remember, this is I. Well, this is n goes from 1 to infinity. This is not a sequence of partial sums. This means we have a1 plus b1. That's the first term. Plus a2 plus b2, right? Plus a3 plus b3. Plus a4 plus b4. And then that goes forever. Parentheses go away. a1, b1, a2, b2, a3, b3, and so on. Regroup your terms. Put your a's together. a1 plus a2 plus a3, and then add your b's. b1, b2, b3. This goes forever. And sure enough, this portion is just simply an. And the next portion is simply bn. Here's what we mean. Here's your summation of an plus a summation of bn. And that actually is proving at least the sum portion. You can do the same for the difference. And then if you said, can you prove the constant, right, times a term? Well, yeah, that's pretty simple. That's CA1 plus CA2 plus CA3 goes on forever. Just factor out C. Just factor. And then you get the constant times the summation of an, because this is an infinite sum. Again, this is my summation an here. Anyway, not too hard. This is property 3 and property 1. You guys can finish property 2 if you like. But these are kind of common sense sort of properties that I want to mention to you guys as well and give you a little bit more examples of what we did today and how to use these properties. Anyway, it's more of a working example. And so I hope you guys enjoyed this. And I'm going to upload it and convert it to 1080p and yada, yada. And I'll, hopefully you guys get this announcement. So see you tomorrow morning.